Good day, everyone, and welcome. My name is Klara Mestrovic, and I will be moderating this very important session on showcasing scientific and societal breakthroughs on EuroHPC supercomputers. This is the last plenary session of this year's summit, and I believe we are all here very happy to be here and to present our work. As you may know, we in the JU procure world-class supercomputers, some of which you may have tested in the demo lab, and also quantum computers, which different technologies you may be able to see in the quantum tunnel, also here in the conference area. As Anders mentioned in the opening session of the first day, we procured this infrastructure precisely in order to enable access to European users coming from academia, industry, and public sector, precisely to contribute to the scientific and societal breakthroughs, in order to enhance the quality of life of everyone here. Today, we will have very interesting speakers. We will start with a keynote session. Then we will have some insights coming from the JU colleagues, and also then the demonstration of 3 successful projects that were running on our infrastructure. After which we plan to have a short Q&A session, and then the closure from our Executive Director, Anders. Okay, I think we are ready to start. As an introduction to our keynote speaker, we would like to showcase a video from CERN that will showcase their scientific and societal breakthroughs. Please. Perfect. So I'm pleased to announce our keynote speaker, Enrica Porcari. Please welcome her on stage.
Thank you. Thank you very much, and good afternoon, everybody. My name is Enrica Porcari. I'm the head of the IT department at CERN, and I'm very glad to be able to share with you some of the work that we do scientifically and how this can apply to society across not only this group, but across the world. So you may have seen from the, sorry, I have to change the slides. All right. So CERN is the world's largest laboratory for particle physics. And our overall goal is to understand the most fundamental particles and the laws that govern the universe. You will see from this slide here a set of circles. Those are the accelerators, the largest one being our latest accelerator, the Large Hadron Collider, which is our flagship accelerator, and is supported by a number of smaller, older accelerators that currently work as kind of accelerating path to make sure that the large accelerator works. So to give you a bit the perspective of the size, at the bottom, you see that white stripe is the airport of Geneva. And you said the red line is what marks the borders between Switzerland and France. So our accelerator sits nicely between the two, across the two countries. 27 kilometers in circumference, sits about 100 meters underground, and is made of a tube that goes around this circle with 2 beams that contain protons that are accelerated close to the speed of light, 99.999% the speed of light, in an ultra vacuum, so that the particles do not meet air particles and be disturbed by them, and in a very cold environment. The particles are accelerated clockwise and counterclockwise at the same speed, and they meet at 4 different points. The 4 different points are where the giant detectors are. Imagine they're like, how many of you have been at CERN? Okay, so I'm speaking to a large, there is a big cluster up there of people who have been at CERN, but so for some of you this may not sound new. I don't know why you're all clustered together, but it's quite interesting. Maybe you should spread and share with others what CERN is about. But so I'm speaking maybe more to those who haven't been yet, and maybe a refresher to those who have been. So those giant detectors are like massive digital cameras, okay? Imagine size 42 meters in length, 25 meters in diameter. So gigantic digital cameras to take pictures of the collisions. Why we do that? We use the insights that come from research to answer some very fundamental questions, such as why is the universe made only of matter, while we could speculate that before the Big Bang there was a balance between matter and antimatter. So the question is, where is the antimatter gone? And why is gravity such a weak force? Or why there is only one Higgs boson? Could there be others? While we do this research, however, we keep society and the impact that we can have inside. And I'll speak about it in a minute. So as I said, we have 4 points of collisions where these gigantic cameras take pictures of those collisions. The 4 experiments are managed by large worldwide collaborations. Atlas is a general purpose detector and is designed to carry out the research. They range from precise measurement of the Higgs boson. In fact, Atlas and CMS jointly identified the Higgs boson in 2012. And they look for new physics beyond the standard model. CMS, as I said, is kind of the pairing detector, and is also the heaviest collider. It weighs about 14 kilotons. ALICE, which you see here at the bottom left, the red one, studies the properties of the so-called quark-gluon plasma, which is a state of matter that probably existed just after the Big Bang, before protons and neutrons were formed. And the LHCb on the bottom right-hand side studies the asymmetry between matter and antimatter and the interactions with the so-called beauty quark. Now, let's see how these collisions happen. So imagine they have these 2 beams, these 2 bunches of protons traveling at the speed of light that meet at a certain point. What they do when they were lucky enough to make them collide, and to make them collide, we basically compress them through magnets, to quadrupole magnets, to make sure that they stay in line. And we turn them around the circle through dipole magnets to make sure that they steer. And when they manage to hit, they produce more than 1 billion particles per second, which is about 1 terabyte per minute stored in our data center. The real big numbers that come from here is the number of collisions that we generate too much data for us to be able to process it. And this is why, in some of the cases, and we'll talk about it in a second, the technology that we have developed to make sure that we are able to collect as much data as possible. When the data is collected, as I said, you have this about 1 petabyte of data generated at the collision, impossible for us to manage. So what we do, we have trigger systems that allow the selection of this data. However, more than 98% of this data is discarded because the trigger system is not fast enough or accurate enough to be able to identify more. So part of the technology development that we're working with is to trying to find new trigger systems to be able to accelerate our rate of sorting. Once the data is stored in our data center, is also distributed through the worldwide Large Hadron Collider computing grid, composed of 170 data centers in over 42 countries, where the data is duplicated and then studied by the local communities. As I said, some of the challenges of the data that we generate, the Large Hadron Collider works in runs. So we currently in the middle of run 3. Every run lasts about 4 years. In run 3, we have collected more data than in run 1 and 2 combined, which means the amount of data that we're able to store and to generate and store grows dramatically. And with the new innovations that we're putting on the accelerator through the high luminosity run, which is going to be our next one, we expect the data to increase at the factor, tenfold. Therefore, we have a constant need to get better at what we do. We do by exploring quantum technologies, capabilities. We heard in the panel before the opportunities coming in quantum. We have a quantum technology initiative when we looked at quantum computing, quantum sensing, quantum networking, but also we started an Open Quantum Institute, which is looking at how this nascent technology can be best applied to use cases that come from the Sustainable Development Goals. So in a continuous effort to contribute to the development of a technology that is fair and equitable and is applicable to society at large. Also as an opportunity, as I said, of leaving no one behind. We also work very hard on new AI techniques. As I said, the ability through, for example, the Next Generation Trigger project, and looking at new AI models to be faster at sorting good data coming from the accelerator. But we couldn't do all of this just with CERN. So we need to continue nurturing worldwide collaborations with many institutes and many technology providers across the world, and with partnerships like the ones we're here today for. So just a few examples of how some of our collaborations already leverage opportunities coming from HPC. On the left-hand side, you see Atlas, as I said, one of the 4 collaborations, one of the 4 experiments. They already make opportunistic use of HPC resources to supplement the resources that are available through the WSCG and CERN. So the one on the left shows through the light blue and the yellow the percentage of HPC resources that are used by the collaboration. You see quite significant, if I may say. And on the right-hand side, CMS, the graph shows that the partner data centers that are involved in the resource sharing for the collaboration. Traditionally, high energy physics has been an high throughput computing infrastructure type, more than an HPC. However, the growing amount of data we are dealing with, the growing use of AI workflows put in place, for all of that, the increase and importance of HPC in our field is growing. So while we are already exploiting some of the HPC resources, we're putting in place a more deliberate roadmap for integrating HPC needs in our computing models. So a few examples of how we are doing this, because putting HPC centers into our current models is a complex task, both technically but also organizationally. So we're trying to explore a few avenues to turn this complexity into an opportunity. So there is a roadmap that CERN is developing for HPC, which includes a deliberate and stronger collaboration with EuroHPC. Through the OSCARs projects, we're working with other scientific communities to ensure interoperability for the computing requirements of our science. Through spectrums, we're also working with other data-intensive research hubs to develop a common blueprint, a common strategy for a European compute and data environment. Beyond the opportunistic resources that CERN experiments are currently used, CERN participates also actively in 3 R&D projects that make use of HPC, Intertwin, to co-design and implement the prototype of an interdisciplinary digital twin engine. We worked already for a number of years on Biodynamo to build a software that supports scientists to easily create, run, and visualize multidimensional ancient space simulations. And most recently, we entered into a partnership with the Luxembourg Institute of Science and Technology and the World Food Programme to leverage AI technologies to speed up progress towards a zero-hunger world. But I would be remiss if I said that the CERN produces innovations only in IT. There are many other areas of our technology in the accelerator detectors beyond computing that have a direct impact on society. This one is just a set of examples of our applications in the medical field, but there are in arts and other societal areas. We see cancer radiotherapy, where we're using protons and other ions rather than photons, as is traditionally done. We're looking at further development of PET scanning technologies, pixel detector technologies that are used for high-resolution 3D X-rays images for both soft and hard tissues at the same time. Radioisotopes for nuclear medicines that are developed at CERN. And more recently, we entered into a partnership with the World Health Organization to look at how we can model pathogens transmission mechanism for both viral and other diseases that are transmitted by air. This was done through a technology that was initially developed at CERN for controlling of re-entry in the office after the SARS-CoV. Now, let me conclude by saying that there are many unanswered questions in fundamental physics, and CERN is committed to continues in this quest for finding those answers. There are many challenges in the computing landscape ahead of us, from geopolitics to procurement to energy sustainability, that we will surely have been explored in this meeting. And I think we need more than ever to build a common vision and believe in the power of collaboration. So at CERN, we want to strengthen the partnership with EuroHPC and in a strategically important partnership to advance the future of data-intensive science. And with that, I thank you.
Thank you so much. Thank you a lot for your very interesting presentation. Okay, we continue. So the next speakers are Catarina and Dora, the colleagues from the JU. They will introduce themselves and give us some insights on what is happening overall with the allocations that are currently running on our systems. Please go ahead.
So hello, good morning everyone. My name is Catarina Guerreiro and I'm a program officer at EuroHPC JU.
Hello, I'm Dora Marton and I'm also a program officer at EuroHPC JU.
And like Klara mentioned, we are going to give you a brief overview of the projects running in the EuroHPC supercomputers. Okay, so let's start by looking at the number of projects awarded in the last years, 2022, 2023, and 2024. As you can see, we can have a positive tendency and an increment of more than 200 projects per year. In 2024, we awarded more than 700 projects. And if we keep with this tendency, we may expect this year, 2025, to award almost 1,000 projects. I would like just to now focus a little bit on the access calls and to remember, some of you, for others might be something new. So benchmark and development access calls are meant for preparatory activities, and in 2024, the increase on these two has increased, as you can see. And then we have the regular, extreme scale, and the AI and data-intensive applications access calls. So these three calls are meant for production activities. And we had a novelty in 2024. We launched the AI access call to fill a former gap in the previous access modes. This AI call was designed to serve industry organizations like SMEs, startups, as well as public sector entities that are in need of GPU resources. And moreover, this call focus as well in ethical and AI and compliance with the AI Act. And in 2024, 54 projects were awarded under this call. Okay, good. Looking now to the evolution of the compute time awarded. So we have exactly the same years here displayed. And we use the units node hours to measure both the CPU and the GPU node hours awarded. And you can see that in the last 2 years, we have awarded around 44 million node hours per year. And so this is now a reality thanks to the efforts undertaken by the EuroHPC and the European Commission, and of course all of you as well, to make the Europe a world leader in supercomputing. And I would like to highlight as well that the extreme scale access call is by far the biggest contributor. And as the name suggests, this call is meant to satisfy the needs of applications that need a large compute time to run. Sorry, it's not changing. Okay, so coming back here, now looking ahead, 2025 will be an interesting year for us and for our users because we will have the first exascale machine procured by the EuroHPC available to users, and we can expect to have more 20 million node hours, this just in terms in GPU for now, more 20 million node hours available for users per year. Then, of course, we also will have AI factories. It's now a reality. It has been widely discussed and will be available to users on the 1st of April. And let's not forget as well the upgrades of the current systems that have been available. Okay, and coming a little just to 2024 again. So this is how our machines looked like in terms of allocations last year. And so from the petascale machines, Vega, Meluxina, Carolina, Discover, Deucalion, to the pre-exascale ones, Lumi, Leonardo, and Mare Nostrum 5. They have been all up and running and ensuring that our users make the best of these resources. So a big thank you as well to all the hosting entities. But let's not forget that this session is about the users. So who are them? Where they come from? So starting by the gender distribution, so we still have mainly men accessing the systems, and unfortunately just 14% of the principal investigators are women. If this is a topic that interests you, and I hope it does, we have an afternoon session about HPC and gender balance. And now talking about the research domains, this is not surprising as well. So most of the applications running are from the exact science. And you can see here in green, we have, need to look because I cannot read there. So, but in green we have engineering, mathematics, computer science, and then light blue, computational physics, and as well chemical science and materials. So these are our mainly users. And now I hand over to my colleague Dora, who will explore more in depth the users.
Thank you, Catarina. We continue with the geographical distribution of our users. As you can see, although there are few countries who are more active in requesting EuroHPC resources, almost all of the participating states of the GU are able to secure access to our infrastructure via the big production cores. In the last 2 days, we have heard a lot about the upcoming AI factories. To complete the picture, we show you here that we already have AI projects running on our clusters. The amount we have awarded via this, via extreme scale regular access and the AI and data intensive access cores were more than 8.4 million node hours. The majority of it was awarded via the extreme scale access core, but already a quarter was awarded by the AI and data intensive access, which we have just launched in 2024, so a year ago. Concerning the AI technologies used by the projects running on the GU, on EuroHPC GU machines, the majority are deep learning and generative language modeling. Now, let's focus on the topic of our session, how these awarded allocations were used for. We have projects powered by EuroHPC GU infrastructure, which helps us understanding the interaction within matter. We have many projects about star formations or understanding the processes inside the sun, inside our sun. We have a project researching a novel light source that can be bright and compact all at once, and which opens possibilities to further advance our research in biological processes, to advance our research in how to manufacture chips. We have many projects which about our understanding how fluid functions and works. We have computational models, or we have many projects where the real-life processes are calculated or replaced by highly complex computational models, saving a lot of time and effort. We have a project which helps users to use sign language to interact with computers. We have many projects tackling environmental issues, such as, for example, one which improves the radioactive waste management. We have another project anticipating the sea level, the rise of sea level. And we have also projects improving the everyday life of our citizens, of European citizens. For example, by optimized radiation therapy, we can improve the cancer treatment. And now let's hear about the projects from our real users. So I give you the...
Thank you, Dora. Thank you both. It was very good to see an overview on what is happening. Can you maybe just press one more to showcase? Yes, perfect. Okay, so this is basically a sneak peek into the 3 upcoming demonstrations of the projects running on our systems. So as you can see by the titles, these are very different projects coming from very different fields. And also they were awarded in different access modes that were previously mentioned by Catarina. So we will start with the first one from agriculture. And this is a project that gained access via our AI and data-intensive applications access call. It was covered by Nils Helset. So Nils, please.
Thanks so much for that introduction. Thrilled to be here today and to get to present a little bit about our project and what we've been working on. And I'll maybe just start with a quick intro, but I'm Nils, one of the co-founders and CEOs of DigiFarm. We're a Norwegian-based ag tech startup. We started in 2020, and I'll talk a little bit about the background of what we're doing and how we can apply, or how we applied HPC back to the kind of farm level. And maybe I'll just jump straight into it. So I was actually born and raised on a farm just an hour northeast of Oslo, and I took over that family farm 10 years ago, and I didn't have any agronomy experience, so I tried to kind of optimize the best I could, and I realized that, you know, farmers struggle with a lot of things, of course, but, you know, there's a lot of data fragmentation in the industry. We have a large lack of automation, and agriculture is still one of the least digitized industries. And as a farmer myself, you know, I have all these digital platforms that I use for, you know, subsidy declarations, crop insurance, variable rate, your agronomist, soil sampling. And the problem is typically those data sets don't talk to each other. So when I set about to try and kind of figure my own farming challenges out, I realized that we had to start with the most fundamental data layer. And it sounds very niche and simple, but it's boundaries. So field boundaries is the kind of fundamental data layer to precision ag and any in-field analytics. And typically what we've been kind of struggling with before is what you see here. So these blue lines are something called common land units from the USDA. We have similar data sets in Europe called LPIS, the Land Parcel Identification System. But they're basically, these, as an example, these are 32 million boundaries in the US, which were manually drawn in about 16 years ago. And over time, you can see they don't reflect which actually planted areas. And that causes a problem. And of course, they haven't been updated because it's very difficult to draw these boundaries every year. So we set out to develop an AI model, or a deep neural network model, that first of all upscales satellite imagery data. So we leveraged Central-2, which is the highest publicly freely available optical data out there from the European Space Agency. It's what you see on the left. It's a wonderful data set. The problem for us was that it doesn't have enough resolution spatially to be able to detect boundaries and objects in the picture. So we developed this model that now super resolves this data from 10 meter, which is what you see on the left, and to 1 meter per pixel, which you see on the right. And this enables us to see the boundaries and of course then detect them. So what you see in the white here is what we built as a model that automatically detects field boundaries and planted areas. So we use kind of vegetation data in the season to be able to do this. And you know, when we look, you know, and of course there's commercial grade satellite data that we could use out there. It'd be very expensive for us to do so. You know, we looked at that, and now, you know, we have much lower cost in terms of input data for this. And of course, we also simulated if we were to draw boundaries every year, as the existing solution is. It takes a lot of time, but it's also very expensive in terms of manpower. So today we detect boundaries at a much higher accuracy and in the season. I'll get to the HPC stuff, but a question we get a lot on the super resolution is whether it's real. And we did an independent study with the Oak Ridge National Laboratory, and also was presented at the ARD conference last year. in San Francisco, where one of our US partners looked at using the super resolution for detecting ships in Long Beach, California. And you can see the original image on the left is one of the ships that's docked, and the AIS points, which are GPS points. Very difficult to see anything there. And then you see the super resolution, which is the middle picture, where it's not perfect, but it's able to reconstruct a lot of the width and length that you see of the AIS points. So validating that there's stuff that we maybe don't see with our eyes, red, green, and blue, but there's 12 spectral bands in this that we're able to reconstruct and provide additional data. And then, when we started this, we didn't realize how important training data was. I still think it's a bottleneck for us, but we've had a team of 28 people. So all these white dots are basically manually drawn field boundaries based on the 1 meter over the last 4 years. And now we've delineated over 3 million manually drawn boundaries, about 5 million hectares of data. And we continue to do so. I think it's still no shortcut for us, and it's really what makes these models perform the best we can. As agricultural areas are so different everywhere in the world. But what we've been able to do is delineate a large chunk of the agricultural land. Europe was our primary market, and then US and Brazil, and you see Africa's not covered yet because it's very difficult, so we're still working on that, but I think we come a significant long way. And now on the HPC side, so I remember when we started, this is our first touch point with HPC. I remember I read a Medium article back in 2020, I think, that said owning your own hardware was cheaper than running cloud, and we thought it'd be a good idea to buy, so we bought it and realized it was a big mistake. It's very difficult to, well, first we put it in our office actually, and it made a lot of noise, so we bought like 8 RTXs 3090s back then, made a lot of noise, very hot, and then I had to move it from the office. I moved to the basement of my farm, and it heated the house, which is great. But then, of course, you need to maintain it and service it and everything else. So, yeah. But this was our first kind of experience, and from there on, we were lucky enough to get some commercial cloud credits, of course, through different startup programs and the NVIDIA Inception program. But very early on realized that we need to have a good R&D infrastructure for us to be able to actually run these models and train the best models we can. And this is where, of course, the Sigma 2, the NCC, and Roger and the team has been incredibly supportive for us to kind of, through this journey over the last 3 years, building an infrastructure, which now, last year, we were lucky enough to get funding for this EuroHPC and be able to train our models on Lumi, which made a significant difference. And now I think we've gone through some growing pains in figuring out what infrastructure we use and how to optimize, but for now I think we will continue to build in this way that we're doing now. And when we look at the benefits, of course, one is that, when we used to, I remember back in the day, we used to train models on these deep neural network models on K80s and P100s and V100s. And it used to take so long for us to train and figure out if it was working or not and reiterate and optimize. And just the ability, it was such a breath of fresh air, of course, running on Lumi, the ability to have results really quickly to know if it's working or not, and then reiterate and keep doing R&D. And for us as a commercial business, still a startup, it was really important for us to cut that time down as much as we could so we can commercialize it. And the other thing we saw is we were able to increase our accuracy on the output, how accurate we detect field boundaries significantly. And as our models grow and training data and kind of frameworks expand, it's that makes a big difference for us commercially as well. So, and of course, we had no idea about HPC when we started in 2020, and just the ability to get the support of creating our infrastructure and knowing how to run and optimize CPU and GPU and everything else has been incredible, both from, of course, Sigma 2 and EuroHPC has been just really, really valuable for us as a business. So, and today, we have a very heavy kind of workload, but we run inference on over 600 million hectares of field boundaries every month. We run this super resolution from 10 meter to 1 meter across 1.6 billion hectares every month. So we have a very big need and demand for HPC and GPU still. And I don't see this slowing down anytime soon for us. So, but it's creating our competitive advantage, and we certainly see that output in our commercial output too. And you know, what does this data mean? You know, we commercialize this through APIs, so we don't sell anything directly to farmers, but we work with enterprise clients, so both agribusinesses and governments, and they will integrate it on their side. And today we have 55 clients across most of the value chain. You know, we work both on the machinery side, which uses input data, of course, for doing variable rate or path planning, A/B lines, variable rate. I mean, prescription maths, of course, but also on the production side, you know, seed production side for knowing seeded acres in the season. And then further down the value chain, we've been doing a lot more work on, of course, subsidy programs. So now we work with 6 paying agencies in Europe, which use this data set as a pre-filled geospatial aided application. Basically, when farmers apply for subsidies, they don't have to draw them manually, which is often inaccurate and causes a lot of monitoring costs for the agency, but actually having the in-season planted area delineated for verification. And of course, crop insurance and finance. But and we've been lucky enough to have some success over the years, but we were named the top 20 startup by European Space Agency. And of course, we were very lucky, much due to EuroHPC and Sigma 2, to also be participating and winning some of these HPC awards last year. And that's it, actually, yeah. So, but yeah, thank you very much for the opportunity, and we're incredibly grateful for the support we've received, and it's certainly had a real commercial difference for our models and business, so thank you.
Thank you so much. Thank you very much. So now we have our next presenter, Pedro Alexandrino Fernandes. So his project comes from biochemistry field, and he gained access via our regular access call. So please.
So good morning to everyone. So first of all, I'd like to thank the organizers for inviting me to show our work in this wonderful conference. In particular, Catarina, Dora, Klara, and Pauline for hosting me here. I'm very grateful for that. So I'll talk about tackling a terrible disease, which is snakebite envenoming, with the help of supercomputing, and show you how supercomputers can accelerate drug discovery in this particular field. So basically, snakebite envenoming is a very old problem. So what you can see in the bottom is a papyrus which comes from ancient Egypt, which is the first research paper about snakebite envenoming. It's a wonderful paper that has 2,600 years old, the manuscript itself, even though the knowledge has more than 4,000 years old, because it's a copy of a copy of a copy, and that it's written the date of the original research is more than 4,000 years old. And you can see in top left, the deadliest snake in Egypt is Egyptian cobra, which it was extremely feared from ancient times, is still today, even though, like today, the cobra is also a subject of fascination. It was also a symbol of divine power and symbol of the domination of the king in the delta of the Nile River, so the lower Egypt kingdom. And you can see it in the crown of the pharaohs, the Egyptian cobra, the symbol of the power, divine power and domination of the king over the delta of the Nile. At the same time, you can see, I don't know if you have resolution to see, but in the right-hand side, you see the interior of a pyramid of one of these pharaohs with something very typical, which is hundreds of spells against snakebite. And these hundreds of spells against snakebite show you how much they fear snakebite in ancient Egypt. And, well, after 4,000 years of continuous research, we still can't manage the problem. The problem is still far from being solved. And how important is the burden? So the burden is extremely important. We have estimations about 2.5 million envenomings by snakes every year, an estimation of between 81 and 138,000 fatalities due to snake bite, more or less 500,000 disabilities, including mostly amputations. And this tragedy happens mainly in Africa and in the Indian subcontinent, and affects the poorest people of those countries, because usually affects people which are very far from the cities, people in very remote regions, agricultures in very isolated areas, because it's on these areas that snake bites exist. is on these areas that people live on the field. So are these people very, very poor farmers that mostly have the burden of snake bites? And to show in comparison with other neglected tropical diseases, you can see in yellow that snake bite envenoming in the top is the deadliest neglected tropical disease on Earth. It kills as much people as the other 19 neglected tropical diseases together, as recognized by the World Health Organization. I also added some numbers in blue to make a comparison for you to see that snake bite envenoming kills more than any war. It's killing more than the Gazan war. It's killing more than the Ukrainian war. I only included Ukrainian casualties. I didn't find solid data for Russian casualties. Include Ukrainian casualties, you can see that snake bite envenoming kills much more people than the Ukrainian war. It kills more people in car accidents in the United States and the EU together. This number is only for the European Union, but if you add the car accidents in the United States, join the two, still snake bites kill more than all these car accidents. This is really enormous tragedy. But we all know that there are antivenoms. It's part of our common knowledge. There are antivenoms against snake bite. And if there are so many antivenoms, why they are not working? Why there are so many persistent deaths due to snake bites? Basically because these antivenoms have very, very important limitations. The first is that they are very complex to produce. To produce an antivenom, you need to immunize horses. So you need to give a small amount of venom to a horse, and then slowly, month after month, increase the amount of venom that we inject in the horse until the horse gets fully immunized. It will take 7-8 months. After 8 months, you can give 5 times the lethal dose to a horse, it will not feel it. So it's totally immune. And once you get the horse immunized, you have to take some part of the blood, some liters of blood, and purify the antibodies and give the antibodies to the victim. That's how it works. But for that to work, you need hundreds of horses in a farm. For some factories of antivenom in India have 2,000 horses. So you can see how complex and costly it is. Then the second thing is that it's a biological treatment. So it needs cold storage and it needs cold transportation. So if you live in a village in a remote part of Africa or in Asia, you need a truck with a refrigerator to bring the antivenoms to the village, and you need a constant refrigerator to keep the venoms in the cold. And many times these villages do not even have permanent electricity. They don't have infrastructures to keep the venoms at cold temperature. And if you store them at room temperature, in a few months, they are dead. They will not work anymore. And they are also very costly. So they can cost between 5,000 to 50,000 euros for a treatment. Also because you need to give them in the intensive care unit. You cannot give them on the field. Even our biologists in Europe, when they go to the field to study snakes, usually they don't bring antivenom. They know they cannot take antivenom in the field because typically an antivenom triggers an anaphylactic reaction. And so the person has like 50% of probability from dying from the snake because half of the times the snake does not inject venom. He just wants to frighten the person. He wants to hold the venom for hunting. So it's 50% of probability for being envenomed. And if you take the antidote, it's 50% probability of dying from an anaphylactic reaction. But if you do it in the intensive care unit, the medical doc can give adrenaline and cool down an anaphylactic reaction and then give another shot of antidote. Then you can have another anaphylactic reaction. It can give another shot of adrenaline and oscillate between the two for 2 or 3 days and control the problem. But you cannot do it in the field. So adding all of these, the treatments became very expensive. This leads to very important shortages in poor regions and basically the total incapacity of these farmers to be treated. Because most of these farmers, they live with 1 or 2 euros per day. How can they pay hundreds of thousands of euros to be treated? And even many times they can't even reach hospital alive. If they reach the hospital, many times the hospital does not have the antidote. And if they have the antidote, they cannot pay it anyway. So they just die because they are poor. They lose children, they lose legs, hands, etc., and die just because they are poor and nothing more. So we need something completely new to treat snake bites, something radically new. An antidote that is stable, that you can put in every village in Africa and Asia, that can be stored at room temperature, that many times in average over 30 degrees, and keeps functional for years, and they can be administered without danger in the field. It is affordable. It's very cheap that people can pay, or at least we can produce and offer without too much costs in all these regions. That's what we are trying to do. And why it's so difficult to develop this kind of medicines? Basically because, poison dart frogs, it's very beautiful frogs that you find in South America. The venom is just one substance. Or puffer fishes that Japanese eat in the restaurant, and when they are not properly cleaned, they die. I don't know if you know it. It's very typical from Japan, and is a delicacy. It's just one substance, the venom. But the snakes have an extremely complex venom. It's not one substance. It's like a mix of venoms. There are many venoms inside the venom, many different toxic substances inside the venom. It's one of the most complex biological cocktails that nature ever created. It's really terrible. And among all these toxic substances, they act in tandem, they act like a team. Everyone does one part of the job to kill the prey and to arrest the prey, to paralyze the prey. But really deadly are about 5. 5 can kill by their own. The other ones just help for the killing or paralyzing the prey. And so what we need is to block these 4 or 5 key components. And so we are trying to develop is a pill. It's very stable, very cheap, with an active component for every one of these 5 very important toxic compounds of the snake bite that can be stored in a local village, that can be taken in your pocket, that when a farmer or a child is bitten in the field, can take immediately the pill and block the action of the venom. And a pill that works for every snake species, because as you know, the traditional antivenoms, that you have, they only work for the snake species that you use to immunize the horse. And if you give the wrong antivenom, you can kill the person very easily. So imagine that you are in India and you are bitten by a snake and you come to the hospital and the doctor asks you that you have been bitten by a naja or a bungadus fasciatus. And you say, well, I'm not sure, I don't know. And then your probability of survival decreases by 50%, just because you don't know. Distinguish two snakes. It's very complex. But with the pills, they will act probably in any snake. Most probably in almost every snake. You don't need to know the snake species. And so we assembled a global team from 4 continents to try to move this idea just from conceptualization to the final pills, of commercialization, to free distribution. And this team is working together for tackling this problem, and at the foundation of the team, and at the foundation of the creation of this new antidote is EuroHPC joint undertaking. So we are on the basis of everything. So if we fail, everything will fail. If you have success, maybe the process will have success. But we are on the foundation, we are on the base. We are the root of the process. And specifically, this supercomputer, Vega, which is where we have been running our calculations, is at the root of the process. As you see, the snakes are very suspicious. They don't like Vega. They fear that their seeds will be unveiled by Vega, but we don't desire any harm to the snakes, just to protect ourselves, so we're sorry. So running calculation Vega, what we understand now is how the toxins of the venom work, how the venoms kill the person, how the venoms kill the animals, how the venoms destroy our cells. That these technical, physiological aspects were very poorly understood. Many of them, there are no experimental tools to dig into the molecular aspects. But with computer simulations, we can do it. But we could not do it in the past because these computer simulations are very time-consuming. For example, in blue, you could see a toxin, one of the worst toxins, we call it PLA2, destroying a cell membrane. Here you can see the chemistry of this toxin that destroys the cell membranes. It kills the cells by destroying the cell membranes. So we could dig into the chemistry, atom by atom, electron by electron, understanding how he cleaves the components of the cell membranes and kills our cells. If it's acting on our kidneys, you lose your kidneys. If you act on your brain, you have a brain hemorrhage. If you act on your muscles, you have paralysis and necrosis. So they're very, very toxic. We took about 2 to 4 million core hours to do this. More chemical simulations to understand how these toxins are destroying our cells so that we can understand how to block it. Because as you know, knowledge is power. If you know your enemy, you can tackle your enemy. So if you know how these toxins work, we know how to block them. But for this, we need EuroHPC joint undertaking infrastructures because this kind of calculations takes millions of core hours. This is another toxin that digs holes on your cell membranes and kills the cells. So the toxin is the blue molecules. So in these simulations, we could understand what they do. We could see them inserting in the membranes and digging holes. You can see a hole opening in the cell membrane. Now the cell is dead. Now there is no hope. Because now we understand how they work, and then we can tackle with this problem. And so at this stage, what we are doing is that we are looking for, we looked already for 1 billion molecules, 1 billion chemical compounds that we believe are chemically stable, that can be synthesized, they are biocompatible, they are not toxic, and they can be administered orally. So if they take it orally, it will distribute through the whole of your body. And from all of this, we selected a number, about 300, that seem to be very, very powerful. And this, because we know how to block these toxins, so we believe this compound will block this PLA2 toxin, for example. And as I'm talking now, my colleagues in the Liverpool Institute of Tropical Medicine, UK, are purchasing these compounds to test them in vitro and in animals to try to see which one are most powerful to continue building up this drug cocktail to treat snake bites. So the project ran in the EuroHPC joint undertaking. It's already passed to experimental level, and now we are running more for more toxins of the snake to make the full cocktail. So in summary, snakebite envenoming is a terrible disease. It kills more than any war that's going on the planet in terms of fatalities per year. It affects essentially the poorest people on earth, people that cannot demand change. They don't have a political voice. They cannot complain. They are illiterate. They cannot organize and make association to complain for their government to have better conditions to treat for snakebite because they are so poor, illiterate, and isolated. And so they just die because they are poor and nothing more. And nobody cares, to be honest. It's very sad, but it's the truth. So these breakthrough drug candidates are being discovered in the EuroHPC joint undertaking. So we believe that we can have a transformative solution, and we can tell you that we'll continue for as long as it takes. Doesn't matter how many years trying to build up this cocktail, but I'm confident that we'll succeed and we'll deliver. And finally, I just want to acknowledge the people which has been working in this project. Maria Ramos, which I worked for 25 years now, all these postdocs and PhD students. Anne Oliveira is now working in a pharmaceutical company here in Krakow. I met her a few days ago. And our international collaborators, the photo credits, these amazing pictures were taken from Rupankar, a wildlife photographer in Assam in India, and EuroHPC joint undertaking, without which nothing will be possible. And for your attention also. Thank you.
Thank you very much. Very interesting, very nice. Okay, let's hear from our third speaker. And then later we will pass. I believe the audience will have a lot of questions. These are very interesting projects. But now we hear the third speaker, and then we will move on to this. So the third speaker, Lucio Meyer, he will join us online. I hope the connection will be good. And the project is coming from astrophysics, and they were awarded via the Extreme Scale Access Call. Lucio, please.
Thank you very much for the invitation. I hope you can hear me well. It's really a pleasure to be here talking, even if I'm online. So I'm going to talk about the TGSF project. This is about the turbulent flows in astrophysics and how they actually impact the formation of stars, which is a central aspect of astrophysics today and over the last 20 years. Next, please. So this project comes after 8 years of development of a new code, which is called SPH-Hexa. There's also a collaboration between different institutions, my university in Zurich and my group, and the University of Basel computer science group of Florina Ciorba, and also a team at the Supercomputing Center in Switzerland, CSCS, and many collaborators across the world that have also helped us during the project, and was funded by PASC over the past 8 years. Next, please. The collaboration is very multidisciplinary. We have been able to build this code through a diverse team of people involving computer scientists, astrophysicists, and cosmologists. Next, please. The ambition of this project was pretty high since the beginning. We were awarded a 22 million node hours allocation on LumiG. And with that, we wanted to leverage our code to really understand much better than ever done before how star formation works. This is a central topic in astrophysics, as I said, and I will try to convey some of the open problems and how we managed to tackle them, or we are going to tackle them through this simulation that we were able to carry out. There is also high interest in understanding large-scale simulations from the computer science point of view, so measuring essentially the behavior of hardware during the execution of the simulation. So also for computer science, this was a very ambitious project. Next one, please. So the code that we have used, SPHX, is really unique in our field. It's the first code that has been built really from scratch to work efficiently on GPUs. Most codes in astrophysics have been refactored for GPUs in the last few years, but none of them has been really conceived for GPUs. And for example, one aspect that makes SPHX unique is that we are able to couple efficiently the solver for fluids, which is done using a particle-based solver, SPH, with the solver for gravity. And in astrophysics and cosmology, gravity is fundamental, is in the driving force of many of the processes that we see happening in the universe. And a fully scalable gravity solver on GPUs, which has been developed through the Cornerstone Octree framework, is really a unique feature of SPHX. Next, please. So star formation. Star formation happens in molecular clouds. These are clouds of gas which permeate our galaxy everywhere, and we think all galaxies are also made in the same way. Here you see the pillars of creation. It's a beautiful image of the Hubble Space Telescope. In these clouds, stars are born. We see them with the telescope. We see the young stars coming out of this pristine gas in the dense clouds. Now, the scales here vary a lot because a single star is located at a scale that is about 10 order of magnitude smaller than the scale of this molecular cloud. So if you are running a simulation to model this system, you really need a huge number of resolution elements to cover a huge range of scales, so large domain and high resolution. And star formation is central for understanding not only stars, but also many other things in the universe. Next, please. Turbulence, for example, is one of the regulating processes of star formation. But star formation, when it happens, it also affects the formation of galaxies. When stars form, eventually some of them, the bigger ones, explode as supernovae. They release energy into galaxies, and they are actually entering in the cycle of energy inside the galaxy. So without understanding star formation, we cannot understand galaxies. Next, please. If you dive down at smaller scales, we have planets forming inside the smallest regions of the clouds. These are happening around stars. But in order to understand the formation of planets, and therefore even the emergence of life, I would argue that you need to understand the primary actors first, which are the stars. Next, please. So there are many big open questions in our field. One of them is really fundamental. What sets the masses of stars? We have stars with different masses. The sun is typical, but we have more massive stars, and we have also much smaller stars, even 100 times smaller than our sun. We have stars in binaries, in multiple systems, and we have stars that are single, like our sun. What sets that? We know that the interstellar medium is turbulent, and turbulence clearly plays a role in the formation of stars, but we don't really understand how does it regulate star formation. And then we also have a question about the chemical composition of stars and of star clusters. We see diverse composition of stars across our galaxy, but we also see that when stars are born together in clusters, they are all very similar in composition. What is the reason for that? Next, please. All these questions require large domains in the models because you need to resolve all these scales. They require a large number of resolution elements because you want to capture the physics at all these scales. You also need high time resolution because there's a lot of dynamical processes happening, so you need to solve the equations in a time-dependent fashion. And you also need to trace fluid elements to understand how things evolve in time from one place to the other place, which needs a code that can do a Lagrange treatment of the fluid like a particle-based code. And that's what SPH-Hexa does. Next, please. So the predecessor simulation of what we have achieved on LumiG has been run a few years ago on SuperMOOC using a completely different method, a grid-based, a mesh-based code. That simulation was great at the time. You know, it marked really a new milestone, but it didn't have the opportunity of looking at the effect of gravity because it was too difficult at the time to incorporate gravity in a code like the one that was used at the time, Flash. But in our code, as I said, the gravity solver is a key aspect, and it's also an aspect that makes the simulation much more physically interesting. And because of the way it was written on GPUs, we can really start and be bold and run simulations that are as big as the ones that were run previously without gravity, but this time with gravity. Next, please. So the way we generate the initial conditions is quite general and is also typical of the field, but is also done in a much more efficient way computationally because it's built in the code. So they are basically generated in situ from the same simulation code that then solves the equations. And initially, we have an homogeneous box with boundary conditions so that we can essentially model a piece of the interstellar cloud as a representative aspect of all the cloud. And then, we have to steer it because we know that clouds are turbulent. We see that, we observe it with telescopes. So we steer the turbulence at the beginning of the simulation. And then we let the system reach a sort of steady state, which we measure in terms of the Mach number, how fast the fluid is moving relative to the typical velocity in the cloud. And then Mach number is kind of reached after some relaxation phase. And then at that point, we start the physical simulation that will really give us the answers, hopefully, for our questions. Next, please. So we have run and completed most of the simulations that we had in mind to complete. The one that is clearly a first-timer already in the field is the one that we have highlighted here, the 5,000 cube run with subgravity. This level of resolution, 5,000 cube particles, cube because it's in a three-dimensional setup, has never been achieved. So we have the opportunity now to analyze the simulation and understand the combined effect of turbulence and cell gravity for the formation of stars. There are also bigger simulations that we have been running for a smaller time, not yet with cell gravity. The 10,000 cube, which was the goal of the simulation project, has been run for a short time, but will be continued afterwards. But most of our simulation program has been completed and is actually been completed faster than we thought because in the meantime, the code has evolved. We introduced a new aspect, which is very crucial, the ability to follow particles with individual time steps. And as you can see in this table, the actual time that the simulations took with this new piece of algorithm was smaller, significantly smaller in some cases compared to the estimated time before we actually executed it. Next, please. When we started the project, we knew already that the scaling abilities of SPH-Hexa on Lumi were really satisfactory, and that's basically the line that you see at the bottom of this plot. But as the code evolved during the execution of the project, the throughput per number of nodes became much higher. So with the individual time steps, we went up to the top of this plot. You can see the blue dot at the top. That's what we are able to do now. So the number of particles, particle rate, basically per GPU node went up significantly. And so now we can complete the same simulations essentially at least 3 times faster than before. Next, please. Visualization is part of understanding the results of the simulations. And here in this video, you can see the main feature of this type of physical system. So the existence of turbulence that is triggered at large scales that propagates to small scales. And you see formation of eddies that continuously acquire denser regions and then they disappear and then they reform again. This is what happens without cell gravity. When you add cell gravity, the denser pockets that form due to the turbulent eddy evolution will actually lead to the formation of stars in most cases. Next, please. A unique feature of SPH-Hexa, which I mentioned at the beginning, is the fact that it is a Lagrangian code because it uses particles to model fluids. And because of that, you can follow fluid elements over time and answer questions like, if this stars form in that place, what is the reason? What properties of turbulence actually made it happen? And if it doesn't form in another place, what properties of turbulence did not make it happen? So this nonlinear behavior of turbulence now it actually translates into the formation of stars in some places and in the non-formation of stars in another place, is really something that you cannot understand without a Lagrangian code. This was a limitation also of the previous bigger simulations done in the past, like the ones at SuperMOOC, which didn't have the ability to follow naturally fluid elements like we can do with SPHX. Next, please. We also care about the energy consumption in our simulations, so we track that through the whole projects. The energy consumption, of course, is relatively high, but because we are using a machine that, like Lumi, our carbon footprint and our energy footprint is really as small as it can be. And we are planning for the future to improve actually the energy efficiency of our simulations by looking at aspects like controlling the frequency of the GPUs in real time. The computer science part of our team is actually working on that, and they actually published a paper recently showing a tool that actually can do it during execution. Next, please. And the other aspect that is now starting is the analysis with new tools. We just were awarded just last month a new project from the Swiss Data Science Center, which will actually increase our team with the aid of experts of machine learning, and we will build a new pipeline to analyze the simulations in a way that has not been done before in the field. We have a huge data set now, thanks to the simulations on LumiG, and this is ideal. This huge data set is an idea to train a machine learning pipeline and analyze correlations between fluid properties, especially for the turbulent flow aspect, in a completely new way, and understand turbulence not only for star formation, but really also dive into aspects of the theory of turbulence that are still not clear in general for fluid dynamics. Next, please. And let me conclude by saying that we are really grateful that we were able to run these big simulations on LumiG. It will lead really to a jump in knowledge in the field. The analysis has just started, but will continue for many months from now. And so the scientific results will come certainly in the next few months, more and more. And the SPHX framework is really generous, so we can run large simulations on machines like Lumi, also for many other applications in astrophysics. Here you see some from galaxy formation to planet formation to the collision of stars to the mergers of supermassive black holes that release gravitational waves. So we have many potential new projects that could run on machines like Lumi in the future. And I thank you very much for listening.
Very good. We're looking forward to the scientific results for sure. Okay, this concludes the three speakers of the projects that we're running on our systems. I think I can speak for everyone. This was very interesting, and it's always very good to hear about the success of our projects. So now it's time for some short Q&A. We don't have a lot of time, but I would like to invite the audience if you have any questions for our speakers. Here, first row, JU.
Hello, Linda Gesenhus from the EuroHPC joint undertaking. First of all, thank you for the presentations. I think it's amazing what all of you are doing. I have a question for Nils. You mentioned that the EuroCC National Competence Center actually helped you to get on the system. So how did this work? How did it help your project?
Yeah, great question. And yeah, I mean, our process started with Sigma 2 and National Competence Center like 2022 maybe or something like that, and they helped us in the beginning. You know, they have their own national infrastructure course, Saga and Betsy, which we started to run processes on and knowing how to run on GPU and being efficient. So I think just that experience we brought into, of course, the EuroHPC and the process we had on Lumi. And of course, there's national allocation. We also had the ability to run on Lumi before we started this large-scale project. So they've been incredibly supportive, and I think it'd be very difficult for us to do it on our own because, you know, we're 54 people. We're very small, like very little HPC experience. So internally, so the ability to have that external support was significant for sure.
Thank you. Any more questions? No? Okay. If I may ask, so question for both of you here, do you plan on applying in the future for your HPC calls?
So we have applied recently for Vega again, and we are granted 26 million core hours. So we are continuing this project against snakebite, and we think we'll continue to apply until we have this problem settled. it can take still a few years. And without EuroHPC joint undertaking, nothing is possible.
And yes, absolutely, same thing. We also recently applied, and I think it's like opening Pandora's box for us, right? Like you can kind of see what's possible. And I was showing the map earlier, and there's stuff, lots of areas missing that we want to get better at, and you constantly see that, you know, it's, yeah, we have an increased kind of requirement for GPU. So yeah, absolutely, we will continue.
Okay, that's very good to hear. Also now when you mentioned that you have things to improve, so what are the limitations that you experienced about using our infrastructure, if any?
Well, the first one was we ran a lot of our stuff on NVIDIA, of course, chips. So AMD was a process for us to kind of get running there on Lumi. But once that was solved, it was all nice and easy to do. And to be honest, once we started training models, we got our infrastructures all set up. It was pretty simple and smooth, actually. So I don't have any. I think still there's work to be done for us to be more efficient and optimize the processes and everything, but that's a continuous journey. So, but the actual model training and everything we had was yeah, very happy with it.
Very good.
Yeah, with us everything is working fine also. So at the beginning we have some difficulties in compiling the codes and optimizing the codes, but the Vega team has been very supportive. We also need to adapt our codes and our way of calculating things to finish calculations in 2 days, 1 day, because usually in our local cluster, we take simulations for 1 month or 2 months, which is impossible in a HPC center. But we have adapted to this, and thanks to the help of supporting teams, everything went very, very smoothly, and is running perfect.
Very good.
I strongly recommend.
Very good. Anyone from the audience, maybe? No?
Thank you for your talk. Just wondering, for the speaking of snakebite, do you envision any other, let's say, technology advancement, like say quantum docking, or let's say deep learning with, I don't know, let's say virtual screening could help in the future? Like, how do you envision these in your future work?
Yeah. So we do almost all of this. So when we search for these 1 billion molecules, we work with virtual screening, with quantum docking, a little bit with machine learning. So that's how we reach these compounds that are being purchased to be tested in Liverpool.
Okay. And another question from here. How did you find the application process? So you both ran on applied to different calls with a different process. So how did you find the experience, like from the application process until the end, after you ran the simulations?
Yeah, I think we've done some like European or Horizon, and we did the EIC Accelerate before and some ESSA projects, so we have some experience like with the applications. I think if we were an SME or startup with no experience, it'd be a little bit daunting, right? But I think it's a pretty simple process actually. So I don't have any immediate feedback. Yeah, I think it was all right. Yeah, actually.
I agree, totally agree. So it's quite simple and straightforward compared to typical applications in European projects. Much simpler, straightforward. We can focus and finish the application in a few days. In particular, if you already have the benchmarkings. Mm-hmm. So it's very simple, very straightforward. And for me, it's perfect.
Great. And this is a very good point, I think, also for the audience, for any future users and also existing users, just to keep in mind that especially for these big access calls, that it's recommended to apply first for benchmarking calls to test your codes and to run properly. This makes it easier, I think, later as well. Also for the evaluation committee, for the technical assessment as well, and later when onboarding the project, I think we can all agree on this. Great. Any questions, maybe from the audience? No? You're shy today? Okay. Well, I think it's fine. So you said you don't have any feedback. I would still ask you to give us some feedback, if possible, even if it's just, oh, you're doing great.
We'd love to get more GPU hours. I'd love that. But otherwise, I think it was smooth.
Yeah, no, for us, it's perfect. So I really, it's not a question of being nice, but I have nothing negative to say. We have we got enough hours for our projects, what was attributed, what was needed. No more, no less. So I think everything is perfect. I just hope that in the future we can continue having the same level of assistance we have up to now. This is the only thing.
No, wonderful. Thank you so much for this. So I think this concludes our session for today. I would like to thank everyone once again, to the speakers, both here and online, also for the audience, both here and online. But before completely closing it, I would like to invite the audience after lunch to go to our parallel sessions, and also to highlight maybe something that is connected to this concrete plenary session is our plenary session that the peer review team will be there, and also our Access Resource Committee Chair and User Forum as well will be there to provide insights on access opportunities and user needs. So maybe this is something that is connected to this session. Okay, and I would now like to invite our Executive Director, Anders Amjesen, to formally close the session. Thank you so much.